So I want to talk about, before we get started in today's lecture, we're going to talk about the state pattern, which I didn't download the slides yet. Uh, but got to talk about lab just a little bit. We hit this Project 2 primer, this point of sale primer, and it didn't go great. It didn't go the way I had hoped. I had a better vision for this assignment. And, I live by a theory where if a student does poorly on something, especially in this context, if a student does poorly on something, that's their fault. If a group of students in a particular breakout room does poorly on something, that's the TA's fault. If the entire class does poorly and the lab just doesn't go the way it should have across the entire class, well, that's my fault. That's on me. So I don't think I had a good design for this lab, obviously, because across all the lab sections, it just didn't go the way I wanted it to. So just a heads up, you can expect for Project 3 Primer, I am going to change the structure of the primer labs. They're, what I'm thinking, I don't know exactly what it'll look like. I'll decide by the time we get there, of course. But what I'm thinking right now is that for each of the lecture tasks, each student in your group is going to have to come up with a test case and then present that test case to the group and say, hey, the TA will say, here's this lecture task. Are there any questions on what's being asked? Take 5 minutes, think up a test case, and then you can share that test case with your group. AI free. I even said in this document, in the document for lab yesterday, you are expected to have the same test cases as the other students in your breakout room. So if you have the same test cases as somebody in your lab breakout room, I'm fine with that. If you have the same test cases as somebody in a different breakout room, I'm not okay with that. So I explicitly said I'm going to back off of AI on this lab, but apparently I don't know if people didn't read that or if I didn't make that clear enough. But I will back off of AI here, and you can share your test cases within your lab group only. So that's what I intended, and the goal of yesterday's lab was for everybody to have test cases for all of the lecture tasks coming out of lab. So you can use what's called test-driven development, where when you're writing your code, you already have your test cases, so you can write some code, hit the green button on your tests, and see how that code is doing on your tests. This should be replacing submitting to Autolab at this point in your careers. The whole reason why we learn testing is because it helps you. It helps you save a ton of time. So if you write your test cases and use those to help you write the code, and then use the debugger when your test cases fail and you don't know why, you will save tens of hours on each project. This project might take you 30, 40 hours if you don't use proper testing. It should only take you like 15 or so, or maybe less, if you use proper testing and proper debug use. And the whole idea of the lab was to really force you to write the tests first and feel the benefits of writing your tests first and using test-driven development. What happened in lab was mostly silence. What I heard from the TAs all day yesterday was that they get in their groups and no students talk. And then I asked students about it in office hours yesterday. I saw quite a few students who didn't have test cases. So I'm like, well, what'd you do in lab? And they're like, I didn't do shit. I just sat there and worked on my project while the TA was talking about something else. I'm like, first of all, why? Second of all, why'd you admit that to me? It's like, why? What is going on? So anyway, lab didn't go great. So there'll be a change in structure. One thing I do want to specifically address, a legitimate reason why somebody said this, that one of the TAs brought up, is that they thought that the other students in their group were quiet because they knew what was going on and they didn't have any questions. I'll tell you right now that is false. Unless you just happen to have one exceptional group, that is false. The majority of you, the bulk of the class, does not know what's going on with this project yet. You will by the time the project's over. You'll get there. But the majority of the class doesn't know what's happening with this project yet. There's a lot of moving pieces. There's a lot going on. That's why we dedicated a 2-hour lab to getting you up to speed on the project, because there's a lot to this project. There's a lot going on with it. Your classmates don't know what's going on. For a specific stat on that, a total of two students have completed all the lecture tasks so far. And there's quite a few students working ahead, reading ahead in the slides, watching last semester's lectures and everything. 2 of them have completed all of the lecture objectives. Your classmates are in the same boat as you. The The idea, you've probably heard this before. If you haven't, this is something you should keep in mind. Whenever you have a question in a class and you're afraid to ask it, just remember probably most of your classmates have that same question. And that was the case yesterday. I think there were quite a few of you who had questions that you wanted to ask, but you were feeling like, oh, everybody else already knows the answer. I'm going to look like a fool. No, they're in the same boat. They want to ask those questions too. Somebody's just got to step up and ask the question. Be like, TA, what is going on? And then you can talk about whatever was causing you trouble. Because most of my TAs, like, they didn't know what to focus their time on because there was no dialogue. They felt like they were just presenting. And unfortunately, we lost some time on that one. And now we're losing more time with me going over it. But I just wanted to mention those points. If you don't know what's going on with this project, well, the lab, we missed that chance to get you all up to speed. But that's expected. If I expected everybody to know what's going on with the project, this primer lab wouldn't exist. I would just remove this from the schedule and do something else with that time. That exists because I don't expect you to know fully what's going on with the project. You can't answer LT5 when you're still on LT2, then ask questions when the TA is talking about LT2. Did you ask questions about it? In office hours, I got a lot of questions about LT2. And my first question was, did you ask your TA this? Like, you got to ask your TA. And same in lecture. Like, if you're not understanding what I'm talking about, ask questions. Because I don't know what you don't know. Like, just by doing this a while, I have good ideas of where everybody's going to be. But I don't know for sure until you ask me. Anyway, I'm done with that speech. I never like giving those speeches. That one was less harsh than I've given really harsh speeches before, which I really don't like doing that. But let's get into the state pattern. And specifically, I'll call it by name, the Imposter Syndrome. If you're feeling like that, like, I'm not going to ask this question because everybody else knows what's going on because they're not asking questions. They're probably thinking the same thing as you. It's tough to fight the Imposter Syndrome, but I'll say one more thing about this is me and my colleagues, we actually talk about this quite a bit, the Imposter Syndrome, feeling like you don't belong where you are, feeling like you're not good enough to be where you are. And we all also get that from time to time. Like, I sometimes go into a lecture going, I'm not qualified to do this. What the hell am I doing here? Hopefully you don't agree, but maybe you do. Some of you will. Like, it's a real thing. It's a real thing dealing with the Imposter Syndrome. The one thing that helps me, and the advice I like to give, is just remember that that's normal and that most of your colleagues are feeling the same way. We all get that from time to time. I had definitely had it as a student. I still have it as a professor. It never really goes away, but you learn how to manage it. And talking to other people and realizing that you're both equally lost can often help, as strange as that might sound. So let's talk about everyone in my program has Imposter Syndrome. Yeah, exactly. Everybody's got it. There are a few students, maybe those 2 students who have all the lecture tasks done, don't have Imposter Syndrome yet. But once they get into like 331 or operating systems, it'll hit them. It'll catch up to them as well. So don't think you're off the hook just because you're doing well in 116. Okay. All right, 10 minutes, that's enough of that. Let's get to some content. The state pattern. So the state pattern, we're going to use this to reinforce inheritance and polymorphism that we learned over the last 2 lectures. So as we're doing this, I'm going to focus on the inheritance and polymorphism, these object-oriented programming concepts, as we talk about the state pattern. The state pattern itself, it's cool, but it's not super important in your career. But we're using this to reinforce polymorphism. So always focus on how polymorphism is being applied as we go through this. And the word of the day is state. I will say state, maybe not a billion times, probably not as much as I said reference in the other lecture, but state is the magic word today. So the lecture test today, and I'll be up front, LT5, you can do this lecture test without the state pattern. It is possible to do this one without the state pattern. You cannot do LT6 without the state pattern, without doing some really fancy advanced stuff. So as you're doing LT5, keep in mind how you're going to use the state pattern for LT6, and also today's content is going to cover LT6. You'll be able to do LT6 with this concept, though you might not really understand the state pattern enough to be able to complete LT6 just after this lecture, which is why LT5 is a softer intro into the state pattern. But for this, we're finally going to start working on the self-checkout class. So as you're working on this, you can run the GUI and start hitting the buttons to be able to enter items and simulate a customer walking up to your self-checkout with a cart full of goods and start scanning those items using the number pad and purchasing those items. That's what we're going to start simulating at this point. We're finally building the whole thing. To enable this, we want the add item method, which is going to take a barcode and an item and add that item to the self-checkout's computer and register that as an item that can be purchased. The barcode is a string, and that this will be numbers only, so we can use the number pad to enter these barcodes. So add item registers that item as something that's possible to be bought through this self-checkout kiosk or machine. Receipt lines, which is going to return a list of all of the lines that should be printed on the customer's receipt. So if you go to a self-checkout, hopefully y'all have used a self-checkout before, or at least paid attention as you have a human checking you out at a store. But as you're scanning items, there will be a screen that displays all of your scanned items along with their prices. This should be the final price after any sales, but not including tax. And this is modeled after how these things actually work. For the most part, except bottle deposit, we are counting as a tax, just to simplify things a little bit. This should return a list of items, a list of receipt lines that should be displayed on that screen. So the customer can see what they've scanned and they can watch the prices as they scan, make sure the prices are what they expect. If something was marked 50% off on the shelf, they want to know that it scans as 50% off and not full price. That's what we want as customers, so that's what we're going to build as developers. This should be the price with the sales, but not the tax. Use the receipt line class. There's a class provided. It doesn't do anything, and you shouldn't modify that class at all, but it has a constructor that takes a string and a double for the description and the price of an item. Return a list of those objects of type receipt line, and that's what the GUI will display on the screen, and that's what you should test in your unit testing. Call receipt lines, get the lines, make sure that all the items show up the way you expect. Building the scan functionality. So as the buttons are pressed, when you see the self-checkout class, the way it's set up right now, there are a lot of methods in there that don't do anything. All of those methods are what we call the API of this class. All those methods are, one, called by the GUI, and they're associated with GUI buttons. So the number pressed method that takes an int, if I press the number 7 on the keypad, that's going to call the number pressed with an argument of 7. It's going to call that method. So all those methods relate to GUI elements, either buttons or the receipt lines and display string. That's what's going to be displayed on each of the displays. And 2, you should call all these methods in your testing, and only these methods. So when you're testing your self-checkout class, create an object of that type, and then call the methods that are provided in the handout code. In my testing, I'm going to assume that those methods exist, and in your testing, you should assume that those methods exist and call those methods. Yeah, apple pears iguanas. That's what API stands for. Application programming interface. It's ways that programs interact with other pieces of software is through an API. It is a kind of general term. Application programming interface. So your testing code or my GUI code is going to call the API of your model to be able to access your functionality. So the customer can scan items. They're going to enter the barcode and then press the enter button. So like if I have an item with a barcode of 1, 2, I'm going to press 1, press 2, and then press enter to scan that item, and then that item should show up on the receipt. If an invalid barcode is entered, you should add error in 0.0 to the receipt line. And for this, you can use the get or else method that is allowed, that does not count as simulating control flow or simulating conditionals. So when you get to that point and you're like, how am I going to do this? Remember this hint, you can use the get or else method. If that doesn't make sense yet, you probably just haven't gotten to this task yet. And display string should always return whatever's being typed in as the user's typing. So if the user hits 1, 1 should be returned. The string 1 should be returned in display string. If they hit 2, the string 1, 2. If they hit 3, the string 1, 2, 3. If they hit clear, then that should be cleared and display nothing anymore. And it should start a new barcode after that. And of course, test all this functionality by calling those API methods in the self-checkout class. Now, I will warn you, for LT 5 and 6, there is a jump up in difficulty from LTs 1 through 4. 1 through 4 is kind of like the warm-up. LT 5 and 6. And we're definitely at the point where we're adding features. Implement this scan feature. I don't tell you anything about how to implement that, what variables you need to create, what extra classes you need to create, what extra methods you have to create to enable that functionality. Which the first time you saw that was LT1 with the scanned and time scan methods. I never said it, but you had to create a new state variable to be able to track that number of times scanned. We're hitting that hard here. How do you implement this scanning method? You got to create new classes, create new state variables, create new methods, whatever you need to implement to get this feature implemented. And that's going to be, moving forward in your career, that's what you're going to be doing. It's not write a method that takes this and outputs this and does this. It's going to be implement this feature into your software. Okay. And if there are more questions about that, I'll take them after lecture, but we got to get through some slides. So I want to talk about design patterns. I want to talk about one design pattern specifically. We're going to talk about the state pattern. It's the only one I'll talk about in the course. We do actually touch on a couple other design patterns, but I don't call them by name in this class. We just use them without identifying them as design patterns. But if you're interested in more of these, check out the Gang of 4. That's your search term, which is going to give you all kinds of design patterns that you can use. These are patterns that simplify common tasks that come up in our programming, and specifically using OOP. These are OOP approaches that can be applied to common problems that we face, and the design patterns are designed to have a structure to the solutions and have general solutions to those problems. The state pattern is one of those such patterns. So the state pattern, like I said, we're going to use polymorphism, and we're going to leverage that significantly. So as we're going through this, pay attention to where we're using inheritance and polymorphism to make the state pattern happen. Because what we really want to focus on, what I really want you getting out of this learning objective is polymorphism and inheritance. To be honest, I don't really care that much if you don't fully understand the state pattern coming out of here, but you need to understand inheritance and polymorphism. The state pattern, we're using it to reinforce those topics and show you what I think is a fun application of inheritance and polymorphism. So what's the problem this pattern is solving? What's the common problem we come up with? Well, it's when we have an object that needs to change behavior based on its state. So we do this now. The behavior of an object can change based on the values in its state variables. For example, if you have a string and you call string.split, what split returns, what that behavior gives you, is going to depend on the current state of that string. What characters are currently being stored in this string object? Well, what are those characters? That's going to determine the array that's returned. If you're splitting on semicolons and your string has the state of that string has a lot of semicolons in it, you're going to get a lot of values. If it doesn't have any, you're just going to get one value. It depends on the state. The behavior depends on the state. But that's not going to change that much. What if we want an object to significantly change behavior depending on its state? So we want to change state and have completely different behavior. Like we want the split method to now combine string. Well, we won't do that. But we want the split method to do something completely different, not just look for a token and split each time. We want completely different behavior from that method. How do we do that? Trusty old if statements. We're going to say if we're in this current state, we're going to do this behavior. Else, we're going to do this other behavior. This is the way we do things up until this point. But of course, where this is going, conditionals are banned for this assignment, which you probably haven't felt very much in LTs 1 through 4. But for this, for LT 5 and 6, you're going to be tempted to use conditionals. You're going to be tempted to say if If this, do this. Else, if this, do this. Which, of course, you can't do. Can't do that for Project 2 because I banned it. So this is what we would normally do, though. If I just said, have this object change behavior based on its state, this is what you do. If some conditional that depends on the object's state, if that's true, do this. Else, do something else. And this works. This is just fine. There's nothing wrong with this. And by the way, I'm not making a statement that conditionals are bad by any means. I only ban conditionals to force you to use OOP. It's a good, convenient way to force you into OOP. So this is okay. But what about maintaining this? And specifically, what if we have a lot of different behavior that we want to do? What if we have a lot of conditionals to check that depend on the current state and a lot of different behaviors that we want to be able to do that? That we want this object to be able to do. First of all, this gets painful to add new conditionals. You really have to be careful when you add a new conditional here to make sure that it's not interfering with any other conditionals. Like in the order of these else ifs, they're going to matter to determine which branch you're going to take. And when we add one, so if we add one, we have to retest everything. If we have a behavior 4 we want to add, we have to retest everything. And it's just hard to read. This method is going to get large. Whatever method this conditional is in, and however complex all these behaviors are, I mean, you might have one method that's 100 lines once you start applying this approach. Which makes it hard to read, hard for you to read, hard to debug. I mean, I saw a lot of your Project 1, your Pale Blue Dot application objectives. I mean, some of your methods were pushing 100 lines, and you come to office hours and it's not working, and it's really hard to tell what's not working. And you usually don't get much good help from office hours because it takes us, the TAs and myself, a long time to parse through all that and figure out what the hell is going on. There's a lot going on, and it's really hard to read and really hard to debug very large methods like that. For that specifically, it helps to write helper methods and then call your helper methods. Write a method that computes the midpoint and give it your lat longs, get that midpoint, and then do your next step, things like that. We're going to take that to the next level with the state pattern. So let's get rid of all this. We don't like this. It's gross. It's hard to maintain. It's hard to read. It's hard to test. And let's switch to the state pattern. So the state pattern, instead of changing behavior based on a value, which is a conditional, you're saying if some Boolean expression, then do this. That Boolean expression is going to depend on values. Instead, we're going to change behavior based on types and leverage polymorphism to change the behavior of an object depending on the type of an object stored in a variable. So we're going to defer our functionality to an object of some type, which we won't even know, might not even know. And we're going to ask that object, hey, do your thing, do your behavior. And whatever type that object is, depending on the type, we're going to get different behavior out of that object, which is going to represent the current state of this object that it's attached to. By doing this, we're going to get rid of that whole conditional block, and each of these behaviors is going to be its own complete different method in a different class. So each one of these behaviors is its own method without the conditionals. So what we end up getting is a lot more methods with a lot smaller pieces of functionality. So each method, and you'll notice as we go through the state pattern, it'll be very rare. I don't think I have a single one, a method that's over like 5 lines. You're going to have very short, concise, easy to test, easy to read methods. You will have a lot of them, but you're going to have a lot simpler methods. Each method is going to be really easy to debug and read. Yeah, it's harder to, if I were to sum it up, it's harder to design the architecture for the state pattern, but once you have your architecture down, what classes you want, what methods you want, it's a lot easier to write the methods and implement the methods. So to do this, we're going to leverage some polymorphism. We're going to have an object, the object that we want to change the behavior of significantly, depending on its state. So we're going to create an abstract class for that state. That's going to define an API, which are the methods that can be called, the methods that we're going to ask the state to be responsible for. And then for each different state we can be in, that object can be in, we're going to create a new class that extends the state abstract class and implements the behavior that the object should have in that state. Then we're going to change the object in that state variable. The object is going to have a state variable of type state. And we're going to change the object that's stored in that state to whatever concrete state we're currently in. And then defer to that state for all of our functionality. So whenever the object should do something, it's not actually going to do anything. It's going to tell its state to do something. And then depending on which concrete state is stored in the state variable, that's going to be the behavior that we have in that state. The states are also going to know which object they're attached to. So the states themselves can access the state variables of the object that they're attached to and also change the state, importantly. Some will call a state transition. Is everyone confused yet? Everyone thoroughly lost? The abstract class will be state, or whatever you want to call your state base class. So you'll define the abstract class and you'll call it. I'm drunk. Yeah, I said state a lot of times there. If anybody's keeping up with the drinking game, oh boy. All right, so what's all this actually mean? So let's explore this with an example. That was my technical explanation. Now let's see an example and see what that actually means. What did I actually just say? I said state about 50 times, but what did any of that mean? So let's take a look at this example. We're going to pull in our good friend Bruce Banner here as an example. Bruce Banner, if you're not familiar with him, he's a world-class scientist. He's able to successfully drive a car, go him, and he's not very helpful in a fight. If you get in a fight and Bruce Banner's on your side, you can't really count on him helping too much. He's not going to be able to do very much. But make Bruce Banner angry, and he'll become the Incredible Hulk. The Incredible Hulk has significantly different behavior than Dr. Banner. For one, he smashes cars. He can't drive them. He certainly can't drive them successfully. He's just going to smash cars. And he's great in a fight. If you have the Hulk on your side, assuming he doesn't turn on you and attack you as well, which might happen, but he's actually great in a fight. He can fight quite well, especially compared to Dr. Banner, who can't fight worth a crap. So we have one man, Bruce Banner. I'll call this Bruce Banner Dr. Banner, and this Bruce Banner the Hulk. So we have one man, Bruce Banner, with two significantly different behaviors depending on his current state. He can either be in a Dr. Banner state or a Hulk state. And what he's going to do in each state is going to change significantly. So let's take this example and simulate this in our code. To simulate this, we're going to create a Bruce Banner class, which is the general person for both of these, either Dr. Banner or the Hulk. And that Bruce Banner class is going to have a state. Get ready for this one. It's going to have a state variable tracking the state of Bruce Banner of type state, and it'll actually be named state. I'm overloading that word significantly today. That state variable is going to determine which state Bruce Banner is in, and then we're going to defer all of the behavior of Bruce Banner to the state, and the state's going to determine how he's going to act. So in the code, the Bruce Banner class is going to look like this. We're going to define the state class in the Dr. Banner class on the next slide. But this is what our Bruce Banner class is going to look like. We have 4 methods that we can call on Bruce Banner. We can either use a car. Dr. Banner can successfully use a car. Hulk cannot. Fight. Dr. Banner can't do well in a fight. The Hulk can. We can make him angry, which is going to transition Dr. Banner's state into the Hulk. And we can calm the Hulk down to transform him back into Dr. Banner. Deferring all the power. I never, as much as I talk about the state pattern, I never thought of it that way. Deferring all the power to the state. That is scary. Thinking of it that way in politics. But we're going to defer all of our behavior to the state. And when each of those 4 methods are called, we're going to have this state variable that controls the state of Bruce Banner. And that state, we're going to call those 4 methods and just defer to the state for the functionality of those 4 methods, for the actual behavior. Bruce Banner doesn't have any hard-coded behavior. We don't know what he actually does when either of these 4 methods are called. We're just going to defer to the state, and the state will determine. In the initial state, the state is Dr. Banner. He's Dr. Banner, and we'll get all the Dr. Banner functionality. If this state changes to the Hulk, we're going to get all the Hulk functionality. So let's look at the rest of the code here. We're going to create the state class, which is abstract, which is going to define the methods that can be called on an object of type state. And it's also going to take a reference to a Bruce Banner so that each state is going to know the Bruce Banner object to which it's attached. Of course, there's only one Bruce Banner. Bruce Banner could be an object here. But for the sake of example, I just made it a class. So Bruce Banner, actually I could just make that an object. It doesn't change much. So the state is going to know which Bruce Banner it's attached to and have all 4 of these methods. These are all abstract because each concrete state or concrete class is going to determine what the actual behavior is. So let's start with Dr. Banner. Dr. Banner takes a reference to a Bruce Banner and passes it on to the state's constructor so it knows who it's attached to. So, and then we have to implement, since we're extending state, we have to implement all 4 of these methods. So we implement all 4 of these methods, and at this point, once we have our structure, we have our state attached to Bruce Banner, we have the state API, these 4 methods. We're calling those API methods because we're guaranteed if this is a variable of type state, it has to implement these 4 methods. Calling those methods. Once we have all that set up and we get to the point where we're implementing these methods and actually building and coding the functionality is really easy. I'm going to skip this one for now, this one and this one. We'll talk about those in a second. But the other methods, calm down. What happens when you calm Dr. Banner down? These are the kind of questions you're going to ask. And to relate it to your project, your API are going to be the button presses on the GUI. And if you're in a particular state of your self-checkout machine, there will be a enter press method that you'll implement. And your question is, when I'm in this state and somebody presses the enter button, what should be the functionality of the enter button? So when Dr. Banner, not the Hulk, when you calm him down, what happens? Well, I'm not doing anything creative here. I'm just printing to the screen, but he's already calm. Nothing's really going to happen. What happens when he uses a car? Well, he's just going to drive the car. I don't show the car class. You can check it out in the repo. It actually uses conditionals, so it's kind of gross in this learning objective. But the Boolean determines whether or not he's going to damage the suspension. So he's not going to damage the suspension. He successfully drives the car. Nothing goes wrong. If he's in a fight, well, he's not going to do so well in a fight. Well, what happens when he's in the Hulk state and somebody makes him angry? Well, he's already angry. It's not really going to do much. It's not going to change his state. It's not going to change anything. He uses a car. He's just going to smash the thing. And in a fight, he's still just going to smash the thing. He's going to smash whatever's in front of him. So when we're writing these methods, writing the methods is actually really simple. Even if we're doing real stuff instead of just printing to the screen. Because you're asking yourself, in this state, what's the behavior supposed to be? And you're doing that in isolation. Your code is nice and encapsulated. You're thinking of one thing only. When he's the Hulk, what happens when you make him angry? That's all you're thinking of. When I'm in the initial startup state of my self-checkout machine and somebody hits the number button, what happens? It helps you stay focused on one piece of functionality without having to think about how that interacts with all of your other code and how does it go into this big conditional block of else if and else if, else if, else if. You're not worrying about that. Or where do I even write this code? None of that. You're just saying, okay, when he's the Hulk and this method is called, what happens? What determines what class will enter? What happens with dot state? So like these dot states, I skipped over these on purpose because they're on the next slide. Maybe not the next slide. All right. So the state takes a Bruce Banner object. So in the Bruce Banner class, we want to initialize this first of all. We want to have some initial state. So we're going to say when we first create a Bruce Banner, when Bruce Banner is first born, I suppose, he's going to be born as a doctor, apparently, but his initial state is going to be Dr. Banner. He's not going to start off as the Hulk state. So when we create a new state, the state takes a reference to the object to which it's attached, which we can access through the keyword this. So inside this is ran when we're creating a new Bruce Banner class. So we're calling this through the new Bruce Banner that's being created. So this is a reference to the Bruce Banner that's being created. When we say new Bruce Banner, this is a reference to that new Bruce Banner. This is what's going to be returned from the constructor and that we're going to store in a variable. So this is the Bruce Banner object. We're going to pass that to Dr. Banner, which is going to pass it to the state. And now we have a reference in this Banner variable to the Bruce Banner object that this state is attached to. And it's very important to be able to get our state transitions, which are these two lines that we're talking about. So Dr. Banner has a reference to the Bruce Banner to which it's attached because we gave it to it right here. We passed that Bruce Banner object to Dr. Banner. Dr. Banner has a reference to the Bruce Banner that it's attached to. The only Bruce Banner in this universe. Well, the way our code's set up, we could have multiple Bruce Banners. We'll be in a multiverse. So with that Banner class, we can access its state and behavior, the state and behavior of Bruce Banner. The one we're very interested in here for these, what we call state transitions, is its state variable directly. So we can access Bruce Banner's state, which currently for our setup is going to be a reference to Dr. Banner. Banner.state is actually the same as this. In this case, we can't just use this equals. But I shouldn't have even said that. It's a little confusing. But banner.state is going to actually be this state. But we're going to say, hey, Bruce Banner, your state is no longer going to be me, this Dr. Banner state, this object of type Dr. Banner. Instead, your state is going to be a new instance of the Hulk state. And I need to pass that Banner object to Hulk because Hulk's going to need a reference to the Bruce Banner to which it's attached. So I'm going to create a new Hulk state attached to Banner, attached to this Bruce Banner, and then change Banner's state to that new Hulk instance. This is what we call a state transition. What I'm saying is, through this code, I have all of it here. What I'm saying on this line is that when Bruce Banner is in the Dr. Banner state, this .state is going to be an object of type Dr. Banner. I'm going to call that makeAngry method. That's this method here in the Dr. Banner class. Banner.state, Banner is a reference to this Bruce Banner. .state equals not Dr. Banner anymore. It's going to equal the Hulk. So that effectively changes this state variable, that's the same variable, to a new instance of the Hulk, which means we've transitioned Bruce Banner's state from Dr. Banner to the Hulk. And now next time we call one of these methods, it's not going to be these methods anymore. We've just replaced all of this with these methods. So we have a state transition. Now Bruce Banner is going to have the Hulk methods as its behavior, and we just switched all of the behavior of Bruce Banner to the Hulk behavior, and we happen to do it without a conditional. Now, when Bruce Banner is in the Hulk state, we get the Hulk behavior for these methods because we're deferring to the state. This .state is an object of type the Hulk with a reference to this Bruce Banner. So we call makeAngry, he's already angry, etc. But we call calm down, this .state, which is an object of type the Hulk. Calm down is going to call this method. It's going to access that Bruce Banner and change its state to a new Dr. Banner object, which is going to transition the state of Bruce Banner back to Dr. Banner calm him back down, and now he switches back to Dr. Banner. He has all of this behavior because his state variable named state of type state is equal to an instance of the Dr. Banner class, or an object of type Dr. Banner. This lecture made you understand polymorphism, inheritance, and state. Whoo, baby. It's a good one. Are there any other questions on this example? Oh my goodness. I got 8 minutes left. Okay, I want to get to the end. I'll take more questions after lecture, but could I make the Bruce Banner class abstract? No, because we do. I don't have it on these slides, but if you look at the repo, I do have an example where we do have to say new Bruce Banner. So we do have to create instances of Bruce Banner. He's not an abstract person. If I did like, I could do abstract class Avenger, and then Bruce Banner extends Avenger. I could do things like that. But we actually need a Bruce Banner. Bruce Banner is an actual person that we need to create an object of that type and work with that. We need to put Bruce Banner on the heap. Okay. Cool, but it's always a big but. Why would we do that? is my question. With just 2 states, I would argue, you could argue, and I would definitely argue that this would be easier with a Boolean flag and an if statement. Each of those methods say have a flag that says is the Hulk equals false. When you make him angry, switch it to true. When you calm him down, switch it to false. And each method should have an if the Hulk, then else, and have all the functionality right there. So with 2 states, we don't really see the benefit of the state pattern. But what if we had more states? When we have more states, that's where we really get to see the power of this, because we can easily expand our code without getting that big if, else, with complex conditionals, complex behavior. So what if we added another state to this and introducing Professor Hulk? So Professor Hulk is the same person, the same Bruce Banner, but after he's learned to control his anger. Bruce Banner can drive a car, not quite successfully. He's going to damage the suspension because he's so big, and he's great in a fight. This is a completely different state with completely different behavior. This third state that he can be in, and we have to add the functionality for this. Now, if we have our if statements, if Boolean flag the Hulk equals true, do this, else do this. If we have our code set up like that, it's really going to be difficult to add this functionality. We're going to have to restructure our entire program, and that's going to be a pain. But since we're set up with the state pattern, this is all we have to do. We're going to create a Professor Hulk state that extends our state and implement these 4 methods. For each of these 4 methods, when we implement them for Professor Hulk, we're asking ourselves the same questions. This didn't get any more complex when we're adding this code. We're asking the same questions. When Bruce Banner is Professor Hulk and you make him angry, what happens? When Bruce Banner is Professor Hulk and you calm him down, what happens? When Bruce Banner is in the Professor Hulk state and he uses a car, what happens? He still drives it, but he damages the suspension. What happens when Professor Hulk fights? What happens? So when you're implementing each method, you're still not doing any extra work. You're just asking the same questions. It's the same amount of difficulty as it was to add the first state. And that's what we want from our code. We want code that's easy to expand. When we have all this functionality in a program and we're happy with it, and a customer says, "Ooh, I'd really like it to be able to do this," we want to be able to add those features. And the state pattern lets us add those features without altering our existing code. For those of you venturing into the application objectives, when you have the state pattern set up well for LT6, adding the application objective doesn't make you fundamentally change how you coded LT6. You're just going to add more functionality to the top of it, unless you had poor design for LT6, of course. So notice we didn't modify any existing functionality. We don't even have to touch the Dr. Banner or Hulk states. We didn't change the way Bruce Banner behaves in either of those states, so why would we even touch those? And we did add a new state transition to enter a new state. And for this one, a few different ways we could do this. We could actually change the state class and add a new method to our other objects, our other classes. But what I did here, I added it directly to the Bruce Banner class. I'm going to say this learn control method I'm going to add. No matter what state Bruce Banner is in, when he learns to control his anger, he's going to always transition to Professor Hulk. So I could add learn control and then do this dot state learn control and defer to the state, and then add to the state abstract class a learn control method and have each state determine what's going to happen when Bruce Banner learns to control himself. But for this one, I said, you know what, this behavior is going to be the same regardless of state. I'm just going to put it in the Bruce Banner class and not defer to the state. You could also add it to the state class and implement this as a full method in the state class that does this, and then defer to the state still, but have a default behavior that all the states have. A few different options there, but we always want to transition into Professor Hulk, whether he's Dr. Banner or whether he's the Hulk. If he learns control, he's going to become Professor Hulk. When we're using the state pattern, it's often very helpful to use what we call state diagrams. And this, I'll say this in office hours a bunch. If you're asking me about your state pattern and stuff, I'm going to ask you to show me your state diagram. Just a heads up for office hours. And if you say, I didn't write no state diagram, I'm going to say, write a state diagram. So in your state diagram, you're going to visually display all of the different states that your object can be in, along with the initial state and any state transitions between them. So for Bruce Banner, we have an initial state of Dr. Banner. If you call his make angry method, he's going to transition into the Hulk. If you call calm down, he's going to transition back into Dr. Banner. And in either of these states, if you call learn control, he's going to transition into Professor Hulk. And then once he's Professor Hulk, there's no going back to the other two states. There's no state transition from Professor Hulk, so we have no outgoing arrows from Professor Hulk. These diagrams can significantly help, and obviously for your self-checkout machine, when you get to LT6, draw up that state diagram and then decide for each state, what should the API methods do? How do I implement each of those methods? Decide how to transition between states, and what states overall should exist. Like for self-checkout, that's one of the first questions you have to ask. Like, what are the states? And especially LT6. We'll go over examples, and I'll refer to LT6 quite a bit on Monday. But just a quick primer. When you first create a new self-checkout, what should each button do? That's your initial state. That's all the behavior of the initial state. What should everything do? When I hit the checkout button, there's going to be a state transition because a lot of the buttons change behavior. Whenever there's any button that does something different, that means you have a state transition. So what state should exist in each state? What should the buttons do? What should the methods do? And when do we change states are the things we need to ask. Then draw out your state diagram and start designing. Which brings us back to the lecture task. Right on time.